There are three main factors that control our wind, and the first is called the pressure gradient force, which is abbreviated PGF. And with these, we want to look at how widely spaced our isobars are from one another. And an isobar is going to be a line of equal pressure. So that if we look along this 1008 millibar isobar, this blue line, everywhere along this line will be exactly 1008 millibars in pressure. It's all equal along that line. But the pressure gradient is how closely or how widely spaced are these isobars or lines from one another. When they're really closely spaced, like we see over here on the right-hand side of this image, it tells us that we're going to have strong winds. Because if we have a lot of these isobars in one area, it's telling us that we're quickly changing the gradient over a short distance. And by quickly changing the gradient, it's going to lead to strong winds. But if we're looking at an area where our isobars are widely spaced from one another, like on the left-hand side of this image, it leads to a weaker pressure gradient force because we're changing our pressure much less over a large distance. So this is going to generate very weak winds. This map is probably something that you've seen if you've checked the weather anytime lately. Here we can see these blue lines, those isobars, which are showing us equal pressure along that line in millibars. And we can see that there's an area of high pressure with 1036 millibars of pressure and an area of low pressure with only 996 millibars of pressure. But looking at these isobar maps, we can figure out not only where the wind is going to be strong or weak, but we can also figure out the direction that the wind is moving. So we know that air is always moving from high to low pressure areas. Air does not like to be compressed in high pressure. Instead, it likes to be in a low pressure environment. So just generally, we should know that the air is going to be moving from our high pressure area to our low pressure area. But we should note that wind moves at a 90-degree angle to our isobars. So using this, if we go through at 90 degrees, we would be able to trace a direct route that this wind would be moving as it's moving from Canada down to Indiana and Illinois. But the second major factor that controls our wind is the Coriolis effect. And this is something that we discussed a lot when we were talking about oceans and how our ocean currents work. But with the Coriolis effect, this is where it looks like something that is moving in a straight line is actually being curved because of Earth's rotation on its axis. In the northern hemisphere, it makes things curve towards the right, making a clockwise movement. And in our southern hemisphere, the Coriolis effect causes things to bend to the left, causing counterclockwise movement. Another important control on our wind is friction. But friction is only going to be important around Earth's surface where that wind is rubbing against the solid rocks or water along our surface. And all of this friction of air moving across the very surface of our planet is going to act so that it slows it down. Because the air is actually touching our continents and our oceans, it's going to slow the wind down at the surface. If we look at the upper winds, not the winds along the surface, but the ones that are found higher up in our atmosphere, we'll see that these upper winds blow parallel to our isobars. And we call these winds our geostrophic winds. And probably the most famous out of all of these geostrophic winds is the jet stream. And the jet stream controls a lot of our climate here in North America. But here it acts like a river of air. Like we're going to be able to see water moving inside of a stream. Within the jet stream, we have huge air masses that are moving around in really high altitudes at really fast velocities. So this river, this stream of air moving in our upper atmosphere is moving anywhere between 75 to 150 miles per hour.